We're going to get started. So thank you for coming to our mini symposium on neuroscience in Julia. So we have several talks. So it's a little complicated because we have a talk now for half an hour, and then there's a keynote speaker, and then we reconvene for the neuroscience mini symposium at 3. And the first talk will be given by Lilianne Mujica-Parodi on Neuroblox.jl. And we all had a workshop on Neuroblox yesterday.
Hello. So what I will be talking about actually is primarily the motivation and conceptual framework for what we're doing, because some of the later talks will get into more of the details. Okay. So obviously, this is a team effort. This is the Neuroblox team. On the top row are the co-founders. We have a spin-off, Neuroblox Inc. So Neuroblox is a software platform that is designed to support biomedical engineering applications. So from that perspective, it's optimized for, as you see, mechanistic integration of disorder and treatment relevant targets. So the format of it is very explicitly multi-scale. And the reason for that is because our motivation is the integration of these disorder and treatment relevant targets with actually the diagnostics that are at the top scale. So obviously the mechanisms behind the disorders, as well as the treatments, mostly the pharmaceutical treatments, the targets are at the bottom scale. So here we have patch clamp, let's say local field potentials, EEG, fMRI, all the way to behavioral, the behavioral scale that is associated with the symptoms. But even though the targets are at this scale, the diagnostics, the measurements are at this scale, and the biomarkers are going to be at this scale. So that imposes certain specific challenges, because we're going to need to develop a computational model that can operate at all of these scales and also is causal. So it's mechanistically integrated from the bottom to the top. So there have been, as some of you know, some computational modeling platforms that have tackled similar sorts of multi-scale modeling. Not so many. It's a hard nut to crack. But the first question that anyone working in this space has to address is, what is the scope of my model? And so there is the kind of the extreme view of detail, which is the best material model of a cat is another or preferably the same cat, which means that if we want to model the brain, we would literally need to model every single aspect of the brain. And there have been some approaches that tried to do this and computationally choked, and we're not able to get so far because this approach actually has some pretty significant weaknesses. And one of them is that it, beyond the computational elements of it, it also doesn't really know how to handle incomplete or unknown data. And so the approach we're going to be taking is the one espoused by my cat, Lemma, who takes the view that a computational model's level of resolution is a critical design choice that needs to match the system's goals. And so since our goals are that we have targets at the bottom scale and we have the biomarkers and diagnostics at the top scale, we're going to really focus on the structures, the architectures, the functional components that are going to link those components. But that we're not necessarily going to model everything. There are things that strategically we will be leaving out. Now, within the top scale, you know, what we have access to in humans, who are the individuals who are going to be getting these disorders, you know, we have neuroimaging paradigms, and within the neuroimaging world, you know, people often talk about networks, circuits, computational model. These are words that get tossed around, but in different fields and at different scales, these are used differently. So within the neuroimaging world, when people talk about circuits, what they really mean is networks, and what they mean by networks are correlations between time series that are acquired from different regions of the brain. What people often mean by computational, likewise, is not necessarily what a computational neuroscientist would view as computational. So if a neuroscientist at the clinical scale would think of circuits as essentially networks, a neuroimager often thinks of computational approaches as those that validate these networks across different data sets, different modalities. So they're really focused primarily on reproducibility, reliability and reproducibility approaches, as well as decoding functions. Now, the problem for our purposes, since after all what we're going to try to do is to toggle components at the bottom scale and then ask what are the emergent features at the top scale, the problem with both of these approaches is that both are discriminative, not generative, right? So they're not going to work in terms of simulations. And the ML approaches don't yield systems that are interpretable. So one of the presumed advantages of these ML approaches is they're very high dimensional. But the problem is, of course, that we're not going to be able to then identify what components are responsible for the outcomes. So connectivity does yield systems that are interpretable, but they don't really, that approach falls apart the moment we really start thinking about control circuits. And unfortunately, that's going to be a fatal flaw when we think about disorders. Because what health is from the perspective of most of physiology is the maintenance of homeostasis in the face of chaotic inputs. And so dysregulation is really what happens during disease, and in order to model dysregulation, we have to think about control circuits. So here's an example of a kind of a canonical control circuit in physiology. So this is looking at glucose-insulin regulation. And one thing, that's very obvious here is that there are different points of failure. So the same control circuit can fail in many different ways, and depending on how it will fail, it will give rise to different outcomes in terms of the measurement of the relevant components here. So glucose and insulin are being regulated, but the time series, the dynamics will look very different depending on how the circuit breaks. And those will give rise actually to clinical phenotypes that look quite distinct. So if you look at a type 1 and type 2 diabetic who are untreated, they look like completely different diseases. And it's only if you really understand the mechanism, you understand that it's the same circuit that's involved, it's just dysregulated in different ways. And that provides a very good model for thinking about how psychiatric disorders can actually be implicating the same circuits and yet be dysregulated in different ways. And one of the important aspects of this approach, of course, is that once you have these generative control circuits, you can not just look at the timescales accessible to you during an actual experiment, but you can look at longer-term trajectories that look at adaptation or degeneration. And in the case of psychiatric disorders, this is really necessary. So certainly we know there are neurodegenerative disorders where we know that there's going to be a change that occurs over time. But in psychiatric disorders, that's the case as well. So you do have degenerative disorders like schizophrenia, and then you have cyclic disorders like bipolar disorder and so forth. And so what we want to be able to do is probe concepts like hitting carrying capacity. So if there's a component of the circuit, so for example, if we want to actually assume that bipolar disorder is, the manic phases are associated by an over-release or secretion of dopamine. So dopamine has precursors, of course, and if you're secreting a lot of dopamine, then you're going to deplete the precursors. You're going to hit the carrying capacity that will cause the system to collapse, right? And so it provides a mechanism for probing whether these overshoot and collapse type dynamics might be responsible for the manic and depressive episodes that you see, for example, in bipolar. And so the issue, of course, is that the standard approaches used in clinical neuroimaging that are dependent on correlations fall apart, really, the moment that you start incorporating feedback components, probably to this audience. I don't need to explain why. And instead, computational neuroscience relies primarily on ODE systems, which makes Julia really a wonderful environment to try to tackle this problem. And once we get into the world of ODE systems, of course, we can look at sensitivity to perturbation and control error and all of these concepts that turn out to be very important in the context of psychiatric disorders. So again, not to belabor the point, but the idea here is that once we get into this world of control circuits, we have additional structure that goes beyond who's connected to whom and gets into questions of timing, thresholds, gating mechanisms, and so forth. And so we, at the fMRI scale, develop some of these approaches within a very practical context. So some of my earliest work was working with the US Navy SEALs in developing a neurobiological diagnostic to be able to predict, using neuroimaging, how someone would respond to extreme fear. And so, if you're doing a study on predicting extreme fear, you have to induce fear. And so we found that one of the most reliable ways to do that was to have someone jump out of a plane at 13,000 feet. They had clothing embedded with biosensors. This is actually me, because I was, I'm always like the first to test the equipment before we run the study. This is Duncan, one of our researchers. And so the idea here is that we are going to be able to take these initial measurements, look at how the brain circuits that regulate emotion are responding within this very controlled clinical environment, and then make predictions about how someone would respond to a very highly controlled but also real-world stressor. And so that was a way to fine-tune these circuits and actually ensure that they were working. And what we found is that that the circuit had, as with the type 2 diabetes, type 1 diabetes example, there are many different points of failure for how the circuit can break, and depending on how it breaks, actually that will position you somewhere on the spectrum between anxious to reckless and everything in between. Now, the problem with that circuit is that we have these elements like these gating mechanisms, we have comparators and gains and so forth, which is great if you're thinking from an electrical engineering standpoint, but the brain doesn't use filters and comparators and gains and so forth. And so the question is, if we want to give drugs, if we want to hit mechanistic targets, then those targets need to be able to interact with the bottom scale in ways that are biomimetic, right? So instead, we're going to have to ask, just as electrical engineering has its own computational primitives and capacitors, gains, and so forth, what are the computational primitives of brain circuits? So these are the microassemblies that I was referring to. So here's an example of a very small circuit called lateral inhibition. You have 4 excitatory inputs. The first that hits inhibits the rest. And depending on the tuning and how this is set up, this pattern is ubiquitous throughout the brain, but depending on how it's set up, it's going to give rise to different filtering mechanisms. So when we say that the brain is processing, these are the units, the sorts of units that are used to actually do that processing. So we can have a whole zoo of computational primitives, each one of which gives rise to a particular function. And from these microassemblies, we can then derive composite circuits. So we have these computational primitives. Those are the most fundamental blocks. From those, we can create the composite circuits. And then from the composite circuits, we can use those as building blocks from which we develop larger scale circuits. So that's the fundamental approach behind Neuroblox, which is we have circuits of circuits of circuits, or blocks of blocks of blocks. So here's an example. So here we are giving the Neuroblox brain, this is a simulation, stimuli. So what's happening is it has to look at ambiguous stimuli and decide whether it's one thing versus another thing. So what it's doing is abstract category learning. And so it's going through these different steps. These are then validated across all scales. So this is going to be producing simulations which are then validated in macaque electrophysiology and then in human ultra-high field fMRI. So in macaque electrophysiology, we can validate in terms of the spiking neuron scale, local field potential scale, but also importantly the behavioral scale. So the Neuroblox brain is actually learning. And so one of the very important aspects, of course, is this validation process. And one thing that is concerning, of course, is that in neuroscience, the threshold for validation is often far less than in fields such as physics. So typically in neuroscience, what we do is we take, an estimation data set and a validation data set that are essentially the same, right? So we divide up the data set, half is estimation, half is validation. And actually, if we're a little bit more rigorous, we will use totally independent estimation and validation data sets, but often of the same paradigm or the same population. But a far more rigorous way of validating a model is actually to develop a circuit or a model using, let's say, the literature. In this case, we actually extract information from the literature, integrate it, create these models, but not for any particular task, not for any particular population, then run simulations and make predictions and validate on a data set that had nothing to do with the initial data from which it was constructed. And in this way, actually, our model predicted new emergent behavior, which was then confirmed empirically in the macaque. So we actually discovered new neuroscience, which wasn't previously known. Hopefully this paper will be coming out soon. We discovered the existence of these incongruent neurons. So when the animal is about to make a wrong decision, actually there are neurons that fire selectively to this wrong decision. So obviously it makes sense that neurons would fire selectively to the right decision. Less makes sense why they would selectively respond to the wrong decision. We think this may be actually avoiding local minima by introducing some noise within the circuit. Lots of further questions you can ask, but the interesting thing is that the model was powerful enough to tell us something we didn't previously know. So in terms of pharma, obviously what we're going to do is have to start at the bottom scale. So here we start with ion channels and receptor binding. That's going to give rise to spiking neuron behavior. Those then input into these computational primitives. So if we give a drug that affects dopamine or serotonin or whatever, it's going to then affect the behavior of these basic processing units, and therefore it will affect the behavior of the circuit as a whole. So here's an example. So in this case, the Neuroblox brain is doing an oddball task. So what it's doing is the brain is responding to novelty. So it's learning a particular tone, and then the question is, how does the brain process what happens when it changes? And now what we're going to do is give the Neuroblox brain propofol. And so again, this gets developed from the field, from the literature, information about what is known about these computational primitives, about neuroanatomy and so forth, and then gets validated independently in the rhesus macaque. In addition, we have plug-in units for Neuroblox. So we have these Neuroblox circuits. In addition to the pharma module, we can look at the impact of metabolism on neurotransmitter cycling. For example, this becomes important in lots of different disorders. So certainly in the contexts of brain aging and dementia, where hypometabolism is one of the key mechanisms, we want to be able to ask, how does learning, mechanistically, how does hypometabolism actually impact learning? And memory, but also there are other sorts of applications that are becoming more relevant recently. So many of you know GLP-1 agonists are very widely used now, initially for type 2 diabetes, then weight loss, but one of the unintended side effects is that they seem to have an impact on addiction, for example. And understanding the mechanisms by which GLP-1 agonists might interact with the circuits that are associated with addiction is only possible if you have a way to actually show the integration of these systems. We also have work on deep brain stimulation, which Herman will be talking about later in the afternoon. So in this case, we're working with a neurosurgical team at Massachusetts General Hospital. They implant electrodes in a particular location, and we want to use Neuroblox to be able to assist them with pre-surgical planning. Obviously, what we want to be able to do is not create these models by hand, but do a kind of an automated process. So I think one of the big directions that we've been hearing about in JuliaCon is SciML and the way to automate the creation of these circuits, and this is an approach that we're using also to use information to extract the circuits in an automated fashion. So that would include the circuit the composition, assembly, comparison, integration, and parameter estimation. The parameter estimation becomes particularly important when you're tuning a model. So in terms of the GUI, for those of you who are familiar with Simulink, or the talk that we heard first thing this morning, very much inspired by the tools that are used in electrical engineering. We are going to create circuits. We want to be able to run simulations, have a GUI that allows neuroscientists and clinicians to interact with the model in an intuitive way. In the case of Parkinson's disease, for example, I'm just giving one use case, it's very clear where you want to insert the electrode. But what, for example, if we have a patient with depression? So in this individual, we may have a 67-year-old female with depression, and the problem is that unlike with Parkinson's, where it's very clear where to place the electrode, in this case, there may be 6 or 7 different potential candidate locations for the electrode. And so the question is, how does the surgeon figure out where to put the electrode? And obviously, we don't want this person to just figure it out during surgery. So instead, we're going to do neuroimaging. We then extract individual-specific parameters for that patient, and then use them to populate the model, and then run simulations, putting the electrode at each of those different locations with different stimulation parameters. And then on the basis of that information, we can start to make decisions in an informed way about how to perform the surgery. So importantly, this is a multimodal platform, which means that we can consider the medications that this patient is on, as well as even the diet that she's on. So here's the GUI. So one of the big challenges in the very beginning is that circuits are, they're distributed throughout the brain. And so if you want to see the entire circuit at once, you can't just pick strategically for a particular slice. So what we've done is we've flattened the brain. So all regions of the brain, this is a human brain, doesn't quite look like a human brain because it's been flattened. But all the regions are represented here, and we've tried to maintain the spatial, geometry as much as possible.
Are you able to put it on the light mode? Because there's no contrast where you can.
Yeah. And so here, what is happening is, that you pick neurotransmitters, for example. You can affect receptor dynamics. In this case, once the circuit is built, you can then provide inputs. So the way it's constructed is inputs are on the left and outputs are on the right. So here, you can put inputs that are the deep brain stimulator, but you can also use inputs that are visual stimuli or auditory stimuli or whatever. So what you can do is in silico experimentation, using the platform, that will make predictions, which then can be used to make decisions about how you conduct your experiment or your surgery or your treatment. So ultimately, what we want to do is provide a knowledge integration ecosystem, to provide a platform where lots of different information can be integrated in a principled way. So it's not simply, taking a paper here and a paper here, but not having them be able to speak the same language. One of the advantages of using this blocks of blocks of blocks approach is that because we have, these biomimetic computational primitives that are consistent throughout the brain. So you have a set of these components from which you can derive circuits. The advantage is that all circuits can speak the same language, right? So different circuits will use different components, but different versions of the circuit, they have the same vocabulary and the same grammar. The advantage of that, of course, is that you can then facilitate the integration of circuits, the comparison of circuits, and then you can start to do community-based modeling, where some people are contributing data, other people are contributing different models. You can then automate the comparison of the models with the data and then decide which models need to rise up in the hierarchy in terms of reproducibility and which models need to be discarded. And for all of this, it was a natural choice to work with Julia because the ODE solvers are probably the best in the field, because the speed was necessary when you're doing multi-scale modeling. It's very computationally expensive, so a lot of the work that we've been doing is thinking through high-performance computing elements. And because there's a very strong community of people who are thinking along these same lines, using many of the same tools like SciML and lots of different applications. And so it was very much a natural choice. So I just should mention, if you're interested in learning more, the commercial website is Neuroblox.jl. If you want to find out more about the research, you can go to lcneuro.org, and we are hiring. Thank you.
Hello? Hi, thank you for the talk. I'm thinking about your point early in the talk about choosing the right level of abstraction and thinking about how that relates to the neuroblocks. Like, where are the ways that has been challenging with the system, I guess, is a part of the question. And then, like, the other piece is, how do you enable flexibility in neuroblocks so that you can adapt the level of abstraction if you need to for a problem, or what does that look like?
So one of the primary design choices was in thinking about the whole notion of a computational primitive, right? And the idea is that we needed to build in right from the beginning the circuits that were the microassemblies that were going to be necessary in order to perform ultimately what turns into cognition. So if you don't have those elements, so for example, in other platforms where the focus has been more modeling things like seizures, the focus has been EI balance, and you have a million, neural mass models, which are all identical, and where what you're tuning globally is the EI balance. So if what you're trying to generate is something like a seizure and global dynamics, that may be the right scale to address those sorts of issues. If you're interested in traveling waves, you think about the problem from that perspective. But in our case, the problem was, something like a sort of a first-generation neural mass model will be totally inadequate in thinking through disorders and pharmacological applications, because those disorders and pharmacological applications go beyond glutamate and GABA, right? I mean, most psychiatric disorders and their treatments are implicating things like dopamine and serotonin and acetylcholine. And so we needed a mechanism that had enough structure at the bottom to be able to accept those targets. At the same time, when I use the example of being able to model seizures, so if what you're interested in clinically are outputs that look like seizures, then your top scale can look like oscillations. But if what you're trying to do is to model psychiatric disorders and dementia, then the symptoms that you care about are cognitive, mood, and behavioral. And unless you are eliciting functions at the top scale that address those three components, you haven't done your job. And so those constraints are ultimately what gave rise to a lot of other design decisions.
By the way, we will address some of this also in the next talk, where we talk about next generation neural mass models, which actually have this feature, right? So they connect microscopic parameters of neurons to global average behavior. And we're super excited about this development.
So one of the challenges computationally is that once you are dealing, so if you know that you need spiking neuron stuff happening at the bottom scale with enough specificity to accept these targets, and you need the clinical stuff at the top scale, that's a lot of simulation, right? And so what you want to do is to flatten the circuit at various key parts where you're incorporating a lot of that mechanistic specificity from the bottom scale, the spiking neuron scale, but without simulating it, always from the bottom scale. And so those are called next generation neural mass models. And then the question is, how do you derive those? You know, like you need to have a large repository of next generation neural mass models, and they need to be adapted to different circumstances. And so the SciML approaches that we're working on are a way to automate the generation of those.
Any other questions?
Okay, thank you.
Okay, so let's thank the speaker.